Hello all. So in this video we will be continuing the chapter group. So in our last video what we discussed were some notations and binary operation and 5 examples of binary operation. So this is the second video of this chapter, of this uh, syllabus of abstract algebra group. And please watch this video only after completing the last video, or else you'll be completely blank, you won't get anything. Okay, so after watching the last video only come to this video. Group. Let G be a set together with a binary operation that assigns to each ordered pair of elements of G. So in the last class we had discussed what a binary operation is, how it is getting ordered pair, and yeah, all that. So here the set is G, elements are A and B, binary operation is, here it is, usually it is multiplication. Okay, so AB, it will be denoted as AB. Now we can say that G is a group, the set G is a group only when it satisfies 4 properties. That is, set G is a group under this particular operation. Here it is multiplication, so under this operation G is a group only when it is satisfying 4 properties. First is the closure property that we have discussed in last class. AB, the new member yielded by this particular operation must also be within this particular set. That is, A and B belongs to G, then AB also belongs to A multiplied by B also belongs to G. Second is associative property. For all A, B, C belongs to G, this happens. Okay. Then existence of identity. E belongs to G. In all group there must exist an element E for which it reflect the multiplication with the same will reflect the same element which you used for that operation. That is, if it is for, in case of the set of n, consider the set of n, then let's take the number 7 under the operation of multiplication. Then we know the identity there is 1. Okay, multiplying 7 with which number will gives you 7 itself. That is what identity is. Okay, so 7 into 1 is equal to 7. So in multiplication it is, the identity is 1, and in addition the identity is 0. 0 plus 7 is equal to 7 plus 0 is equal to 7. For all A belongs to G. Okay, fine. Then the fourth property is existence of inverse. For all A belongs to G, there must also exist A inverse that also belongs to G. A into A inverse must give you the identity also, identity of this particular set. So yes, let's say inverse of A is B. That means AB is equal to BA equal to E. In that case we can say B is the inverse of A and A is the inverse of B. Now abelian group. A group G is said to be abelian if, in addition to the 4 properties, that is closure, associativity, existence of identity, existence of inverse, one more property must also satisfy. That is, for being an abelian group, 5 properties have to be satisfied. And the 5th property is commutativity. For all AB belongs to G, A into B must be equal to B into A. A group is non-abelian if there exist some pairs of elements and elements like AB for which AB is not equal to BA. Okay. Now as I said, there are 20 examples in total and we'll be covering 12 in this class. Sorry. The set of all integers, Z, set of all rational numbers, Q, set of all real numbers, R, are all groups under ordinary addition. Identity will be 0. Inverse of the particular number, say A, will be minus A. You can check it with all, all these numbers from these 3 sets. With this set we can take 1. 1 plus 0 is equal to 0 plus 1 is equal to 1. identity is okay for 1, and for -1 also the same applies. Okay, you can check it whether I'm not checking with all the numbers because the video will get more lengthy then. Now second example is that z, set of all integers under ordinary multiplication, is not a group. Identity is 1, fine, but there does not exist any inverse, because according to us the inverse is, say the number a into a inverse must gives identity. Here must give e. Here e is equal to 1. So 1. So if we take 7 is an integer, right? 7 into 7 inverse. It doesn't happen. -7 into -7. Okay, it gives -49. Okay, minus have to be here. Sorry. Next is there exists no integer y such that 3 into y is equal to 1. Right. So next comes the third example. So here we are studying the K-list table. I'll teach you how to draw that. So the subset 1 minus 1 I minus I, complex numbers, okay, of the complex numbers is a group under complex multiplication. So this is a K-list table. This is what? It's a K-list table. And how is it formed? We have the four elements of this particular set are 1 minus 1 I minus I. Same applies here, 1 minus 1 I minus I. You need to write in the same order, okay? And so here it is the multiplication. Here it is the multiplication. I just can denote it with a dot. So 1 multiplied by 1 gives you 1. 1 multiplied by -1 will give you -1. 1 multiplied by I gives you I. 1 multiplied by -I gives you -I. -I, okay. Yes. Next, -1 multiplied by 1, -1. -1 multiplied by -1 gives you 1. -1 into I minus I. -1 into -I. I. Minus into minus plus, so it is I. Then I into 1. I multiplied by -1 minus I. I multiplied by I minus 1. I into I is -1. Then I multiplied by -I. Then that will be +1. Minus I multiplied by 1 minus I minus I multiplied by I. Then minus I multiplied by I gives you 1 minus I multiplied by negative I itself, so that gives you -1. So that's it. So this is how you form a K-list table. From this it is clear that closure property, because all the elements are multiplied here within this, right? And all the answers, all the new members yielded are in this set only. 1 minus 1 I and minus I. These all are in the set. So closure property is satisfied. Associative property is also satisfied. Right? You can check that. Then next is identity element. That means the same number have to be reflected. 1 is the identity element, because you can get that, right? 1 is multiplied by 1, you get 1. 1 is multiplied by -1, you get -1. 1 is multiplied by I, you get I. 1 is multiplied by -I, you get -I. Okay, so the identity is also 1. Next comes inverse. So there is a trick to check the inverse. So we know what is inverse. Say the number A multiplied by this particular inverse, that is A inverse, must give you E. So here we know what is E. E is 1. So let's check through which operation does 1 is yielded. In the case of 1, 1 is yielded here. So the inverse of 1 is 1 itself. For minus 1, sorry, yeah, same. Next for minus 1, that is this number, 1 has appeared here. Okay, so multiplying minus 1 with minus 1 gave you the answer 1, right? So in the case of minus 1, inverse is minus 1. Next comes I. Multiplying I with what gave you 1? 1 is here, okay? So I into minus I gave you 1. So the inverse of I is minus I. And in the case of minus I, minus I into I gives you 1. So I is the inverse of minus I. Yeah, as we say, AB, if B is the inverse of A is the inverse of B. So not these. From Cayley's table, it is clear that closure property and associative property is satisfied. One is the identity element and these are the inverses. Now fourth, the set of Q plus positive rational numbers is a group under ordinary multiplication. 1 is the identity of the element and inverse of A is 1 by A. Got it? Then fifth one, set of all positive irrational numbers. So that is S. Under multiplication satisfies the properties, last three properties given in definition of group. Last three properties, okay? But it is not closed. The first property, it is not closed under the multiplication. Because root is an irrational number. Root 3 multiplied by root 3 gives you 3. 3 is not an irrational number, right? It is in the rationals. So it is not closed, that means it is not a group. Next, sixth, a rectangular array of the form this, okay, is called a 2 by 2 matrix. The set of all 2 by 2 matrix with real entries is a group under component wise addition. You know what component wise addition is. A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2. The identity will be 0, 0, 0, 0. Inverse will be minus A, minus B, minus C, minus D. Okay. Now the seventh one. The set of all Zn, that is, okay, I'll teach you. For all, with the examples you will get what a model and integer and all things are. So for the time, for n greater than or equal to 1 is a group under addition modular. For any j greater than 0 in Zn, the inverse of j is n minus j. This group is usually referred to as the group of integers modular. Okay, so there is nothing complex here. With the example it will get clarified. So consider Z5, 5 elements, right? Zn means n elements. So why the last number is n minus 1 for Zn? Because 0 is calculated in the integers. 0 is calculated here. So 0, 1, 2, 3, 4, 5 elements are done. Now the composition table, the Cayley's table. We know how we did that. In the i's case, right? So 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. In the case of Z, it is addition modular. As I said, okay, so what is modular? With this example, you will get clarified with that. So here, we are adding. You got it now? The answer must be only below to 5. So 0 plus 0 is 0, fine. 0 plus 1, 1. 0 added to 2, 2, and 3, 4. That row is perfect. Then comes 1. 1 added with 0 gives you 1. 1 added with 1 gives you 2, 1 added with 2 gives you 3, 1 plus 3 is equal to 4, 1 plus 4 is equal to 5. Okay, if it reaches 5, you need to start subtracting it with this particular number. This n. 5 minus 5 is equal to 0. Okay, got that. Then 2. 2 added with 0 is equal to 2. 2 added with 1, 3. 2 plus 2, 4. 2 plus 3, 5. So 5 minus 5, 0. Then 2 plus 4 is 6. 6 minus 5, 1. Okay. Then 3 plus 0, 3. 3 plus 1, 4. 3 plus 2, 5. 5 minus 5, 0. 3 plus 3, 6. 6 minus 5, 1. 3 plus 4, 7. 7 minus 5, 2. Then 4 plus 0, 4. 4 plus 1, 5. 5 minus 5, 0. 4 plus 2, 6. 6 minus 1. 6 minus 5, 1. Then 4 plus 3, 7. 7 minus 5, 2. 4 plus 4, 8. 8 minus 5, 3. So this is how addition modulen works. In the coming topics also, addition modulen is really important. You need to do this. I won't be explaining it anymore. Get it thorough here itself. So from this we get 0 is the identity element. And the inverses also. I taught you how to find the inverse in the last class, or in this class itself, I guess. Okay, sorry, bad memory. And let's check. The identity is 0. So where will be the inverse? We know for the number, say a into a minus 1 must give the e identity. Here e is equal to 0, so 0. So in the case of 0, the identity is 0 itself, because 0 comes here. In the case of 1, identity is 4. So in the case of 4, identity is 1. Just check where the 0 comes, okay? Those are the inverses. Not identity, inverses. I'm really sorry for the mistake. Inverses. For the 1, inverse is 0. 0 inverse is 0. 1 inverse is 4. 2 inverse is 3. 3 inverse is 2. 4 inverse is 1. Okay, not this. So this is an abelian group. You know how it became abelian group. A into B is equal to B into A. Here the operation is addition modulen with that. Next is 8th one, the set of real numbers R star, that is set of all real non-zero real numbers, is a group under ordinary multiplication. Identity is 1, inverse is 1 by A for A. 9th one, determinant of 2 by 2 matrix is the number AD minus BC. If A is a 2 by 2 matrix, determinant of A denotes the determinant of A. That is the set of GL 2 by 2 comma R. 2 means it is a 2 by 2 matrix. R means the entries are of real numbers. And here the determinant must not be equal, must be not equal to 0. Then it is a non-abelian group under the operation. This is the operation, okay? Not this. It is difficult to explain this more and more, because these are the basics of matrices and all. So if you are thorough with it, you will get this. These are how we take the determinant and all. Next is, so if we take the product of these two, product of two matrices with non-zero determinant is also a non-zero determinant. Associative property will be verified, like all can be verified here easily. I won't be spoon feeding you all this, okay? The identity will be 1 0 0 1 and inverse will be adjoint of the inverse, okay? Adjoint of the inverse. And this is called a general linear group of 2 by 2 matrix of real numbers. This is really important. What I thought was a star, but it ended up in a trash. Let me try again. So this is really important. General linear group of 2 by 2 matrix over IR. That is real numbers. General linear group. Now 10th is set of all 2 by 2 matrices with real entries is not a group under the operation multiplication because inverse do not exist when determinant is 0. 11th, for each n greater than 1 we define un. So you'll get to know what un is. Un to be the set of all positive integers less than n and relatively prime to n. So un is a group under multiplication modulo, that is, if n is equal to 10, let's check for which order it is a co-prime. For 1 and 10, it is fine. There exists no other. Then if comes to 2, no, because 2 into 5 is equal to 10. So it can't happen. 3, yes. 4, no, because in 4 there comes 2. Which is not possible. 5, no, because 5 into 2 is 10. Then 6, no, it is divided by 2. 7, yes. 8, no, again divided by 2. 9, yes. Okay, so 1, 3, 7, 9 the UN. And the Cayley's table for the same. You know how this works because I discussed it with 2 examples, right? And here it is mod 10. Only difference is that in previous we used addition model and here it is simply mod 10, and I just discussed what a mod 10 is, right? U10, you know, co-primes and all. So in that way you can check this. Next is 12th. The set of 0, 1, 2, 3 is not a group under multiplication model of 4. Clearly 1 is the identity element, although 1 and 3 have inverses, 0 and 2 do not have inverses. This is x4, that is multiplication model, and it is 0, 1, 2, 3, 0, 1, 2, 3, 0 into 0, 0, fine. Okay. 0 multiplied with anything, it gives 0. And for 0, the answer, the identity is 1. It is not yielding. 0 is multiplied with all the numbers, but it is not yielding 1. So there is no inverse for 0. Then comes 1. 0, so 1 into 1, 1, 1 into 2, 2, 1 into 3, 3, fine. 2 into 0, 0, 2 multiplied by 1, 2, 2 multiplied by 2, 4, so 4 minus 4, 0, then 2 multiplied by 3, 6, 6 minus 4, 2, it comes like that, so you can check that. Then 13 also I am taking. From 14 onwards I will be taking in the next class. The set of integers under subtraction is not a group since the operation is not associative. 3 minus 1 is not equal to 1 minus 3. Okay, so that's it for today's class. In next class we'll be dealing with the rest of the examples, that is 14 to 20. Okay, that's it in the next class, and further we are having so much to cover. Okay, but yes, we will. After that we'll be covering symmetries of square, which comes actually under the unit 2, but I'm taking it in this in this leave itself. Okay, thank you.